give the floor to our first speaker, Waseem Abdelazim. This research is part of the big research that's performed at the University of Sherbrooke in Canada. And please start by introducing yourself and like a few sentences about what you are like about your background. Thank you.
Okay, so I'm Waseem Abdelazim. I'm now a postdoctoral fellow at the University of Sherbrooke. I am interested in the design, analysis, and testing of FRP, reinforced concrete members. For example, the column, the reinforced concrete columns, and characterization also of FRP bars. Okay, good afternoon, everyone. Again, it's my pleasure to be here presenting my research today. And again, I'm Waseem Abdelazim, postdoctoral fellow at the Department of Civil Engineering, University of Sherbrooke. I know it was a long day, so I'll try to make it as light as possible. As you know, and as Mr. Chairman said, the last decades have witnessed a rapid innovation in the FRP industry. However, and up to date, the current North American codes have not yet addressed the design of slender FRP reinforced concrete columns. So my research here aims at investigating the behavior of such columns based on experimental and buckling analysis. The presentation, or the typical content of the presentation, is outlined into 6 sections. It starts with the introduction, followed by the objectives and the methodology. The methodology is consisted of the experimental program and the theoretical study. Then the presentation is ended with the main conclusions and design recommendations. Let's get started with the introduction. In general, reinforced concrete columns can be classified either into short columns or slender columns. Slender columns are defined as those columns that suffer a considerable strength reduction due to second order effects, and also can be defined based on the North American codes as or at a slenderness ratio exceeds 22, below which it is accepted to neglect the second order effects, and the column can be designed as short. The current North American codes dealing with the design of FRP members set the slenderness limit of FRP reinforced concrete columns as 22, like steel reinforced concrete ones, disregarding the different behavior between steel and FRP bars. In addition, none of the available North American codes permits using FRP bars in slender columns. And this is, in my opinion, mainly due to the lack of the experimental data. Therefore, my research, or the main objective of my research, is to address the feasibility of integrating GFRP bars as an internal reinforcement of reinforced concrete slender columns. In terms of investigating the general behavior and failure mechanisms, assessing the second order and buckling responses of slender GFRP reinforced concrete columns, and also to develop some design guidelines related to the slenderness limits and stability problems. The methodology to achieve these objectives can be drawn from the shown schematic chart. The research program is consisted of 2 parts, experimental program and a theoretical analysis. The experimental program includes 38 GFRP reinforced concrete columns. Then the study was extended by conducting a theoretical buckling and second order analysis in order to propose some design or some useful design recommendations. All tested columns had the same diameter of around 300 millimeters with different column heights, ranges from 1 meter up to 2.5 meters. And 6 test parameters were investigated in this study. The first parameter was the slenderness ratio in terms of 5 different column heights, in which the slenderness ratio ranged from 14 up to 33. And the second test parameter was the type of reinforcement, as we have 4 slender steel reinforced concrete columns were fabricated and tested at the same conditions as GFRP ones. And the third test parameter was the longitudinal reinforcement ratio, where the reinforcement ratio ranged from 2.2 up to 4.7%. Effect of confinement ratio was also investigated in terms of spiral pitch distance, and the design for spiral reinforcement conforms to CSA S806. In addition to the pure axial loading, 3 eccentricity ratios were applied to develop a complete BM interaction diagram. And finally, we had 2 concrete batches, one for normal strength concrete and the other for high strength concrete. All cages were assembled using sand-coated GFRP bars, and we didn't have any lap splice in all cages. As the mechanical properties of the used reinforcement is listed in the shown table as provided by the manufacturer. All reinforcing cages were assembled and fabricated in our laboratory of materials and structures of the University of Sherbrooke. The fabrication process was started with assembling all GFRP cages, then all cages were instrumented using 6mm strain gauges at the mid-height. Bomb was then used to cast all the specimens. Meanwhile, sufficient number of standard concrete cylinders were prepared from each concrete batch to define the actual concrete strengths. Finally, all columns were cured to avoid any shrinkage cracks. All columns were then moved to the testing lab. Prior to testing, all columns were grouted at top and bottom surfaces to ensure uniform load distribution. Then we used top and bottom steel collars to confine the column at the stress concentration zones and to draw or to plot the lateral deformation of the column during the testing. We used the meters at mid and quarter heights of the column. The column was then aligned into the testing machine and all the instrumentation were connected to the data acquisition system. The loading started with a rate of 2.5 kilonewton per second up to 75% of the expected column capacity. Then the load was continued with a displacement rate of 2 micrometer per second. Excuse me. The next part highlights the main test observations and is divided into 2 parts. The first part is the general behavior and failure mechanism. The second part is the effect of test parameters. Let's start with the general behavior and failure mechanisms. Regarding the axially loaded column, the shown load axial displacement response shows that once the load was applied, the specimens behaved linearly up to around 85% of the column capacity. Then the nonlinear stage started and vertical cracks appeared near 95% of the axial capacity. Once the concrete cover is pulled out, the column capacity dropped within 15%. Meanwhile, the concrete core started to dilate and the spiral strain increased till spiral rupture occurred with or without bar rupture. Regarding the steel reinforced concrete column, the failure was dominated by buckling of steel bars. And in the next slide, this slide, we can show all the failure mechanism of all concentrically loaded columns. We can define that, or we can define the failures as compression controlled failure for all columns, and we didn't get any, or we didn't observe any stability failure. Even for slender columns have slenderness ratio of 33. Regarding the eccentrically loaded columns, the behavior of columns loaded at low eccentricity was quite similar to concentric loaded ones, while columns loaded at an eccentricity diameter ratio equal 0.66 behaved as flexural members in terms of early formation of tensile cracks and large deformation at the peak load. Column tested at eccentricity diameter ratio of 0.33 provided a transition failure mechanisms between the low and high eccentrically loaded columns. Finally, all GFRP bars were intact till the end of testing and were capable to resist high values of compression and tensile strains, compressive or tensile strains. And we can see in this slide the failure mechanism of all tested or all eccentrically loaded column. The second part related to the experimental observation is the effect of test parameters. The first test parameter investigated in this study is reinforcement type, and from the plotted load axial displacement curves and lateral displacement profile, and also the shown failure of the tested steel and GFRP reinforced concrete columns, it can be observed that the behavior of the slender GFRP reinforced concrete columns are very comparable to steel reinforced concrete counterparts. And of course, there is some reduction in the loading capacity, but this reduction in the capacity of GFRP reinforced concrete columns or the relatively higher lateral displacement compared to steel reinforced concrete ones can be considered in the design equations. Regarding the effect of GFRP reinforcement ratio, as we can see from these BM interaction diagrams, increasing the GFRP reinforcement from 2.2% up to 3.3% improved the column capacity at all tested slenderness ratios up to slenderness ratio of 33. The effect of slenderness ratio also can be discussed through the plotted experimental BM interaction diagrams, in which the solid line defines the cross-section strength, while the dotted line defines the slender column behavior. At all eccentricity to diameter ratios, increasing the slenderness ratio from 23 up to 33 increased the second order effects with more pronounced values at an eccentricity to diameter ratio ranges from 0.16% up to 33%. Sorry. The next part is conducted theoretical analysis. Theoretical analysis conducted is divided into buckling, load analysis, and the second order modeling. Buckling analysis was performed considering the tangent modulus theory based on Euler loads. In our theoretical analysis, three approaches were investigated to assess the compression contribution of FRP bars. The first approach is to ignore the bar compression contribution. The second one is to consider the bar contribution. And the third one is a proposed approach is to replace the FRP bars with concrete. The second order analysis performed followed the Zhang and Ting's model, and they considered both the material and geometrical nonlinearities, as we can see in the next flow chart. This flow chart summarizes the analysis process using Zhang and Ting's model, highlighting the geometrical and material nonlinearities. The analysis starts by assuming the column lateral displacement, then secondary moments and curvature can be calculated, and this defines the geometrical nonlinearities. Then the concrete strain is assumed, and the neutral axis is located, and this defined the material nonlinearities. Using this theoretical analysis, we defined the slenderness limit. First, we have to define the stability curve or Euler-Johnson stability curve. This curve displays the effect of slenderness ratio on the column axial capacity based on Euler-Johnson's formulas. From this curve, two slenderness limit can be plotted. The lower slenderness limit determined at 5% strength reduction, below which the column can be safely designed as short, and the upper slenderness limit defines the limit beyond which the probability of stability failure increases. So we have to define lower slenderness limit for the FRP reinforced concrete columns, and also have to define the upper slenderness limit for the FRP reinforced concrete columns. Regarding slenderness lower limit, the shown stability curves were plotted for GFRP reinforced concrete columns based on the aforementioned theories. The dashed line defines the boundary for 5% strength reduction, and the dotted line is for 10% strength reduction. For both boundaries, the 5% and the 10%, the slenderness limit reaches its lowest at an eccentricity to diameter ratio closest to 0.3. This can be clearly shown in the second figure, as it shows, the second figure shows the variation in the slenderness limit with eccentricity to diameter ratio at 5% strength reduction. And the slenderness limit, as we can see, can be defined or proposed as 18 at an eccentricity to diameter ratio of 0.3. And this can be formulated as shown from the shown equation, similar to ACI formula. The proposed slenderness lower limit is adjusted or generalized to include high strength concrete columns based on regression analysis. And the slenderness limit can be found from this equation based on the used concrete compressive strengths. The slenderness upper limit can be defined from the plotted interaction diagram. This BM interaction diagram shows different loading paths for GFRP reinforced concrete columns. Each path have different slenderness ratio, range from 18 up to 100. Stability failure is defined when the column loading path reaches their maximum capacity at a point before reaching the BM interaction diagram. It can be noted that the threshold for stability failure occurs close to a slenderness ratio of 50. This slenderness ratio, which is 50, corresponds to a moment magnification factor of 1.4. Therefore, the proposed slenderness upper limit to avoid any stability failure is corresponded to a secondary to primary moment ratio less than or equal 1.4. Just to sum up, the shown schematic diagram summarizes the proposed design for GFRP reinforced concrete columns. For short columns have slenderness ratio less than 18. Column can be designed as short, replacing the FRP bars in compression with concrete. Slender columns have slenderness ratio exceeds 18. In this zone, column can be designed as slender using the moment magnifier approach stated in ACI 318, considering proper values for the effective flexural stiffness and the stiffness reduction factors. Finally, if the moment magnification factor exceeds 1.4, the structure system should be revised to avoid any stability failures. At the end, from this research program, we can draw the following conclusions. The experimental observations proved that proved the feasibility of GFRP reinforcement as an internal reinforcement for slender reinforced concrete columns in terms of significant compression contribution to the applied loads. A slender GFRP reinforced concrete columns up to slenderness ratio equal 33 exhibited lower capacity but with similar failure mechanisms compared to short columns. All slender GFRP reinforced concrete columns experienced material failure, and we didn't exhibit any noticeable stability failure. And GFRP bars provided high resistance to both tensile and compressive strains. Regarding the design recommendations, a slenderness limit of 18 was proposed, and for columns, for GFRP reinforced concrete columns bent in a single curvature, and this value was generalized to consider high strength concrete, as shown. And a slenderness upper limit corresponding to a secondary to primary moment ratio of 1.4 was also proposed to avoid any stability failure. Finally, the complete research program and related findings can be found in the shown publication. I think it's all of them are already published. Finally, I'd like to express my gratitude to Professor Brahim bin Mukran of course, and all partners in success for the continuous support and valuable contributions. Thanks a lot, Mr. Chairman, and thank you all. Thanks a lot.